Cerium. Cerium is a chemical element with symbol Ce and atomic number 58. Cerium is a soft, ductile, and silvery white metal that tarnishes when exposed to air, and it is soft enough to be cut with a knife. Cerium is the second element in the lanthanide series, and while it often shows the +3 oxidation state characteristic of the series, it also exceptionally has a stable +4 state that does not oxidize water. It is also considered one of the rare earth elements. Cerium has no biological role and is not very toxic. Despite always occurring in combination with the other rare earth elements in minerals such as those of the monazite and bast-nasite groups, cerium is easy to extract from its ores, as it can be distinguished among the lanthanides by its unique ability to be oxidized to the +4 state. It is the most common of the lanthanides, followed by neodymium, lanthanum, and praseodymium. It is the 26th most abundant element, making up 66 ppm of the Earth's crust, half as much as chlorine and 5 times as much as lead. Cerium was the first of the lanthanides to be discovered, in Bastnäs, Sweden by Jöns Jacob Berzelius and Wilhelm Hisinger in 1803, and independently by Martin Heinrich Klaproth in Germany in the same year. In 1839 Carl Gustav Mosander became the first to isolate the metal. Today, cerium and its compounds have a variety of uses. For example, cerium oxide is used to polish glass and is an important part of catalytic converters. Cerium metal is used in ferrocerium lighters for its pyrophoric properties. Cerium doped YAG phosphor is used in blue light emitting diodes to produce white light. Cerium is the second element of the lanthanide series. In the periodic table, it appears between the lanthanides lanthanum to its left and praseodymium to its right, and above the actinide thorium. It is a ductile metal with a hardness similar to that of silver. Its 58 electrons are arranged in the configuration 4f15d16s2, of which the 4 outer electrons are valence electrons. Immediately after lanthanum, the 4f orbitals suddenly contract and are lowered in energy to the point that they participate readily in chemical reactions. However, this effect is not yet strong enough at cerium and thus the 5d subshell is still occupied. Most lanthanides can use only 3 electrons as valence electrons, as afterwards the remaining 4f electrons are too strongly bound. Cerium is an exception because of the stability of the empty F shell in Ce4+ and the fact that it comes very early in the lanthanide series, where the nuclear charge is still low enough until neodymium to allow the removal of the 4th valence electron by chemical means. 4 allotropic forms of cerium are known to exist at standard pressure, and are given the common labels of alpha to delta. Cerium has a variable electronic structure. The energy of the 4f electron is nearly the same as that of the outer 5d and sixs electrons that are delocalized in the metallic state, and only a small amount of energy is required to change the relative occupancy of these electronic levels. This gives rise to dual valence states. For example, a volume change of about 10% occurs when cerium is subjected to high pressures or low temperatures. It appears that the valence changes from about 3 to 4 when it is cooled or compressed. At lower temperatures the behavior of cerium is complicated by the slow rates of transformation. Transformation temperatures are subject to substantial hysteresis and values quoted here are approximate. Upon cooling below 15 degrees C, gamma cerium starts to change to beta cerium, but the transformation involves a volume increase and, as more beta forms, the internal stresses build up and suppress further transformation. Cooling below approximately 160 degrees C will start formation of alpha cerium, but this is only from remaining gamma cerium. Beta cerium does not significantly transform to alpha cerium except in the presence of stress or deformation. At atmospheric pressure, liquid cerium is more dense than its solid form at the melting point. Naturally occurring cerium is made up of 4 isotopes, 136Ce, 138Ce, 140Ce, and 142Ce. All 4 are observationally stable, though the light isotopes 136Ce and 138Ce are theoretically expected to undergo inverse double beta decay to isotopes of barium, and the heaviest isotope 142Ce is expected to undergo double beta decay to 142Nd or alpha decay to 138Ba. Additionally, 140Ce would release energy upon spontaneous fission. None of these decay modes have yet been observed, though the double beta decay of 136Ce, 138Ce, and 142Ce has been experimentally searched for. The current experimental limits for their half-lives are: all other cerium isotopes are synthetic and radioactive. The most stable of them are 144Ce with a half-life of 284.9 days, 139Ce with a half-life of 137.6 days, 143Ce with a half-life of 33.04 days, and 141Ce with a half-life of 32.5 days. All other radioactive cerium isotopes have half-lives under 4 days, and most of them have half-lives under 10 minutes. The isotopes between 140Ce and 144Ce inclusive occur as fission products of uranium. The primary decay mode of the isotopes lighter than 140Ce is inverse beta decay or electron capture to isotopes of lanthanum, while that of the heavier isotopes is beta decay to isotopes of praseodymium. The great rarity of the proton-rich 136Ce and 138Ce is explained by the fact that they cannot be made in the most common processes of stellar nucleosynthesis for elements beyond iron, the S process and the R process. This is so because they are bypassed by the reaction flow of the S process, and the R process nuclides are blocked from decaying to them by more neutron-rich stable nuclides. Such nuclei are called p-nuclei, and their origin is not yet well understood. Some speculated mechanisms for their formation include proton capture as well as photodisintegration. 140Ce is the most common isotope of cerium, as it can be produced in both the S and R processes, while 142Ce can only be produced in the R process. Another reason for the abundance of 140Ce is that it is a magic nucleus, having a closed neutron shell, and hence it has a very low cross-section towards further neutron capture. Although its proton number of 58 is not magic, it is granted additional stability, as its 8 additional protons past the magic number 50 enter and complete the 1g7/2 proton orbital. The abundances of the cerium isotopes may differ very slightly in natural sources, because 138Ce and 140Ce are the daughters of the long-lived primordial radionuclides 138La and 144Nd, respectively. Cerium tarnishes in air, forming a spalling oxide layer like iron rust. A centimeter-sized sample of cerium metal corrodes completely in about a year. It burns readily at 150 degrees C to form the pale yellow cerium oxide, also known as ceria. This may be reduced to cerium oxide with hydrogen gas. Cerium metal is highly pyrophoric, meaning that when it is ground or scratched, the resulting shavings catch fire. This reactivity conforms to periodic trends, since cerium is one of the first and hence one of the largest lanthanides. Cerium oxide has the fluorite structure, similarly to the dioxides of praseodymium and terbium. Many non-stoichiometric chalcogenides are also known, along with the trivalent Ce2Z3. The monochalcogenides Ces conduct electricity and would better be formulated as Ce3 plus Z2E. While CeZ2 are known, they are polychalcogenides with cerium. Cerium chalcogenides remain unknown. Cerium is a highly electropositive metal and reacts with water. The reaction is slow with cold water but speeds up with increasing temperature, producing cerium hydroxide and hydrogen gas. Cerium metal reacts with all the halogens to give trihalides. Reaction with excess fluorine produces the stable white tetrafluoride CEF4, the other tetrahalides are not known. Of the dihalides, only the bronze diiodide CEI2 is known, like the diiodides of lanthanum, praseodymium, and gadolinium. This is a cerium electride compound. True cerium compounds are restricted to a few unusual organocerium complexes. Cerium dissolves readily in dilute sulfuric acid to form solutions containing the colorless Ce3+ ions, which exist as a 3+ complexes. The solubility of cerium is much higher in methane sulfonic acid. Cerium and terbium have ultraviolet absorption bands of relatively high intensity compared with the other lanthanides, as their configurations make it easier for the extra F electron to undergo FD transitions instead of the forbidden FF transitions of the other lanthanides. Cerium sulfate is one of the few salts whose solubility in water decreases with rising temperature, Cerium aqueous solutions may be prepared by reacting cerium solutions with the strong oxidizing agents peroxidisulfate or bismuthate. The value of E varies widely depending on conditions due to the relative ease of complexation and hydrolysis with various anions, though plus 1.72 V is a usually representative value, that for E is 2.34 V. Cerium is the only lanthanide which has important aqueous and coordination chemistry in the plus 4 oxidation state. Due to ligand-to-metal charge transfer, aqueous cerium ions are orange-yellow. Aqueous cerium is metastable in water and is a strong oxidizing agent that oxidizes hydrochloric acid to give chlorine gas. For example, ceric ammonium nitrate is a common oxidizing agent in organic chemistry, releasing organic ligands from metal carbonyls. In the Belousov-Zabotinsky reaction, cerium oscillates between the plus 4 and plus 3 oxidation states to catalyze the reaction. Cerium salts, especially cerium sulfate, are often used as standard reagents for volumetric analysis in cerometric titrations. The nitrate complex 2 is the most common cerium complex encountered when using cerium as an oxidizing agent. It and its cerium analog 3 have 12 coordinate icosahedral molecular geometry, while 2 has 10 coordinate bicaptodecahedral molecular geometry. Cerium nitrates also form 4:3 and 1:1 complexes with 18 crown 6. Halogen-containing complex ions such as Cef4-8, Cef2-6, and the orange CeCl2-6 are also known. Organocerium chemistry is similar to that of the other lanthanides, being primarily that of the cyclopentadienyl and cycloctatetranil compounds. The cerium cycloctatetranil compound has the uranosine structure. Despite the common name of cerium compounds, the Japanese spectroscopist Akio Kotani wrote there is no genuine example of cerium. The reason for this can be seen in the structure of ceria itself, which always contains some octahedral vacancies where oxygen atoms would be expected to go and could be better considered a non-stoichiometric compound with chemical formula CEO2X. Furthermore, each cerium atom in ceria does not lose all 4 of its valence electrons, but retains a partial hold on the last one, resulting in an oxidation state between plus 3 and plus 4. Even supposedly purely tetravalent compounds such as CERH3, CeCO5, or ceria itself have X-ray photoemission and X-ray absorption spectrum more characteristic of intermediate valence compounds. The 4f electron in cerosine, Ce2, is poised ambiguously between being localized and delocalized, and this compound is also considered intermediate valent. Cerium was discovered in Bastnäs in Sweden by Jöns Jacob Berzelius and Wilhelm Heisinger, and independently in Germany by Martin Heinrich Klaproth, both in 1803. Cerium was named by Berzelius after the dwarf planet Ceres, discovered 2 years earlier. The dwarf planet itself is named after the Roman goddess of agriculture, grain crops, fertility, and motherly relationships, Ceres. Cerium was originally isolated in the form of its oxide, which was named ceria, a term that is still used. The metal itself was too electropositive to be isolated by then current smelting technology, a characteristic of rare earth metals in general. After the development of electrochemistry by Humphrey Davy 5 years later, the earth soon yielded the metals they contained. Ceria, as isolated in 1803, contained all of the lanthanides present in the cerite ore from Bastnäs, Sweden, and thus only contained about 45% of what is now known to be pure ceria. It was not until Carl Gustav Mosander succeeded in removing lanthana and diatomea in the late 1830s that ceria was obtained pure. Wilhelm Heisinger was a wealthy mine owner and amateur scientist, and sponsor of Berzelius. He owned and controlled the mine at Bastnäs, and had been trying for years to find out the composition of the abundant heavy gangue rock, now known as cerite, that he had in his mine. Mosander and his family lived for many years in the same house as Berzelius, and Mosander was undoubtedly persuaded by Berzelius to investigate ceria further. Cerium is the most abundant of all the lanthanides, making up 66 ppm of the Earth's crust. This value is just behind that of copper, and cerium is even more abundant than common metals such as lead and tin. Thus, despite its position as one of the so-called rare earth metals, cerium is actually not rare at all. Cerium content in the soil varies between 2 and 150 ppm, with an average of 50 ppm. Seawater contains 1.5 parts per trillion of cerium. Cerium occurs in various minerals, but the most important commercial sources are the minerals of the monazite and bastnasite groups, where it makes up about half of the lanthanide content. Monazite is the most common representative of the monazites, with Ce being the Levinson suffix informing on the dominance of the particular Re-element representative. Also the cerium-dominant bastnasite is the most important of the bastnasites. Cerium is the easiest lanthanide to extract from its minerals because it is the only one that can reach a stable +4 oxidation state in aqueous solution. Because of the decreased solubility of cerium in the +4 oxidation state, cerium is sometimes depleted from rocks relative to the other rare earth elements and is incorporated into zircon, since Ce4+ and Zr4+ have the same charge and similar ionic radii. In extreme cases, cerium can form its own minerals separated from the other rare earth elements, such as cerianite, O2. Bastnasite, LNIIICO3F, is usually lacking in thorium and the heavy lanthanides beyond samarium and europium, and hence the extraction of cerium from it is quite direct. First, the bastnasite is purified, using dilute hydrochloric acid to remove calcium carbonate impurities. The ore is then roasted in the air to oxidize it to the lanthanide oxides, while most of the lanthanides will be oxidized to the sesquioxides Ln2O3, cerium will be oxidized to the dioxide CEO2. This is insoluble in water and can be leached out with 0.5 m hydrochloric acid, leaving the other lanthanides behind. The procedure for monazite, PO4, which usually contains all the rare earths, as well as thorium, is more involved. Monazite, because of its magnetic properties, can be separated by repeated electromagnetic separation. After separation, it is treated with hot concentrated sulfuric acid to produce water-soluble sulfates of rare earths. The acidic filtrates are partially neutralized with sodium hydroxide to pH 3.4. Thorium precipitates out of solution as hydroxide and is removed. After that, the solution is treated with ammonium oxalate to convert rare earths to their insoluble oxalates. The oxalates are converted to oxides by annealing. The oxides are dissolved in nitric acid, but cerium oxide is insoluble in HNO3 and hence precipitates out. Care must be taken when handling some of the residues as they contain 228Ra, the daughter of 232Th, which is a strong gamma emitter. The first use of cerium was in gas mantles, invented by the Austrian chemist Karl Auer von Welsbach. In 1885, he had previously experimented with mixtures of magnesium, lanthanum, and yttrium oxides, but these gave green-tinted light and were unsuccessful. 6 years later, he discovered that pure thorium oxide produced a much better, though blue, light, and that mixing it with cerium dioxide resulted in a bright white light. Additionally, cerium dioxide also acts as a catalyst for the combustion of thorium oxide. This resulted in great commercial success for von Welsbach and his invention, and created great demand for thorium. Its production resulted in a large amount of lanthanides being simultaneously extracted as byproducts. Applications were soon found for them, especially in the pyrophoric alloy known as misc metal composed of 50% cerium, 25% lanthanum, and the remainder being the other lanthanides, that is used widely for lighter flints. Usually, iron is also added to form an alloy known as ferrocerium, also invented by von Welsbach. Due to the chemical similarities of the lanthanides, chemical separation is not usually required for their applications, such as the mixing of misc metal into steel to improve its strength and workability, or as catalysts for the cracking of petroleum. This property of cerium saved the life of writer Primo Levi at the Auschwitz concentration camp, when he found a supply of ferrocerium alloy and bartered it for food. Ceria is the most widely used compound of cerium. The main application of ceria is as a polishing compound, for example in chemical-mechanical planarization. In this application, ceria has replaced other metal oxides for the production of high-quality optical surfaces. Major automotive applications for the lower sesquioxide are as a catalytic converter for the oxidation of CO and NOx emissions in the exhaust gases from motor vehicles, ceria has also been used as a substitute for its radioactive congener thoria, for example in the manufacture of electrodes used in gas tungsten arc welding, where ceria as an alloying element improves arc stability and ease of starting while decreasing burn-off. Cerium sulfate is used as an oxidizing agent in quantitative analysis. Cerium in methane sulfonic acid solutions is applied in industrial-scale electrosynthesis as a recyclable oxidant. Ceric ammonium nitrate is used as an oxidant in organic chemistry and in etching electronic components, and as a primary standard for quantitative analysis. The photostability of pigments can be enhanced by the addition of cerium. It provides pigments with light fastness and prevents clear polymers from darkening in sunlight. Television glass plates are subject to electron bombardment, which tends to darken them by creation of F-center color centers. This effect is suppressed by addition of cerium oxide. Cerium is also an essential component of phosphors used in TV screens and fluorescent lamps. Cerium sulfide forms a red pigment that stays stable up to 350 degrees C. The pigment is a non-toxic alternative to cadmium sulfide pigments. Cerium is used as alloying element in aluminum to create castable eutectic alloys, AlCe alloys with 6/16 weight% Ce, to which Mg or Si can be further added. These alloys have excellent high temperature strength. Cerium has no known biological role in humans, but is not very toxic either. It does not accumulate in the food chain to any appreciable extent. Because it often occurs together with calcium in phosphate minerals, and bones are primarily calcium phosphate, cerium can accumulate in bones in small amounts that are not considered dangerous. Cerium, like the other lanthanides, is known to affect human metabolism, lowering cholesterol levels, blood pressure, appetite, and risk of blood coagulation. Cerium nitrate is an effective topical antimicrobial treatment for third-degree burns, although large doses can lead to cerium poisoning and methemoglobinemia. The early lanthanides act as essential cofactors for the methanol dehydrogenase of the methanotrophic bacterium methylacidiphyllum fumariolicum solvi, for which lanthanum, cerium, praseodymium, and neodymium alone are about equally effective. Like all rare earth metals, cerium is of low to moderate toxicity. A strong reducing agent, it ignites spontaneously in air at 65 to 80 degrees C. Fumes from cerium fires are toxic. Water should not be used to stop cerium fires, as cerium reacts with water to produce hydrogen gas. Workers exposed to cerium have experienced itching, sensitivity to heat, and skin lesions. Cerium is not toxic when eaten, but animals injected with large doses of cerium have died due to cardiovascular collapse. Cerium is more dangerous to aquatic organisms, on account of being damaging to cell membranes, but this is not an important risk because it is not very soluble in water.